So in chemistry, I think one of the main things I try to do is make it relevant, and there are two areas of chemistry that I think are going to be relevant for us. And one is pH balance. That's very important. And can y'all read that screen okay? Is that dark enough and everything? Okay. And then the other thing is polarity. And if we can get through an understanding of those two things today, then we'll add to that the idea of protein structure, because that's going to be crucial to our understanding of cell biology. So if we don't get to protein structure today, we'll hit it tomorrow. I want to make sure we have a thorough grounding in definitely pH and absolutely importantly polarity. Polarity is like the basis of everything we need to do. So that's absolutely crucial. All right, let me see if I can remember how to get a next page. Next page. I have utterly forgotten how to get a next page out of this. There we go. Okay, so to understand pH, you need to have an understanding of what it's measuring and the chemistry of that. So who knows what pH is a measure of? Okay. Hydrogen ions. And how would we write hydrogen ions? We write it H+. Okay. And it's a measure of hydrogen ions in concentration. And when we measure concentration as some kind of amount per volume, typically per volume. And the way we're going to measure amount is, for hydrogen ions, we're going to measure it in moles per liter. So does anybody remember what a mole is? I'm not talking about a little furry animal that lives underground. Not really. It's not a weight. It's a quantity. Okay. So a mole equals the number of molecules that it takes to make the gram molecular weight. The number of molecules it takes to make the gram molecular weight. Okay? And the cool thing about a mole is it doesn't matter whether it's a little teeny hydrogen ion or a honkin' big iron atom. It doesn't matter. The mole is the same. That's one of to me, the miracles of modern chemistry is that a mole is a mole is a mole. A mole is 6.023 times 10 to the 23rd. That's Avogadro's number. And that's not on the test. Just as some chemistry background. Does that ring a bell to anybody, Avogadro's number? Very cool. Okay. So now that I've given you that background of what a mole is, then we can quit worrying about the definition of a mole. What is a mole? A mole is a quantity, like a dozen. What's a dozen? It's 12. Okay, what's a gross? Does anybody know what a gross is? Don't know what a gross is? Oh my gosh. Okay. A gross is a dozen. Dozen. Okay? So in that same category, what's a mole? It's a number. It's a number of molecules. It's a very specific number of molecules. Okay? So if I take 1 gram of iron, I know exactly how many molecules or how many atoms of iron are in it. If I take 1 gram of water, is it going to have the same number of molecules as 1 gram of iron? Yes. Well, no. If I take 1 mole of water, is it going to have the exact same number as 1 mole of iron? A mole is a mole is a mole. Is it going to have the same weight? No. Okay, iron's very heavy, water's not. Is everybody okay with that idea? All right, so now that we have that kind of latched down, in your heads you have some idea of what a mole is, like a dozen. It's a number. It's a big number, but it's a number. then that's our idea of concentration. So if I have a 1 molar concentration of anything, iron, sodium chloride, whatever, then I know I have 1 mole of, if it's sodium chloride, 1 mole of salt in a liter of water. Is everybody okay with that idea? All right, so that's what we mean by concentration. So the abbreviation I use for concentration is brackets. So if I want to say the concentration of hydrogen ion, that's the way I write it. Are you with me on that? Okay? All right. Moving on. What is the molecular formula of water? This is a tough question, I know. H2O. So if I separate out a hydrogen ion from water, what do I have left? If I pull out 1 hydrogen ion, what's left? It's a OH minus. Does everybody see why? If I add those two things back together, I get 1 molecule of water. So if I split a hydrogen ion off of water, what's left? OH minus. Okay, the plus and the minus will cancel each other. And what is this called? Hydroxide. Is that challenging to anybody? Is everybody okay with that? Are we good? All right, so does everybody see that for every hydrogen there is in water, there's also an equal number of hydroxides? It's a 1-to-1 relationship, right? So if I tell you that in water, the number of hydrogen ions is exactly equal to the number of hydroxyl ions, that's not surprising to you, is it? Because we just said if you split it, if you get one, you get one of the other. Are you with me on that? We're going somewhere with this, okay? And that, folks, is our definition of what is neutral. A solution is neutral in pH if it has exactly the same hydrogen and hydroxyl ions. Okay, that's our chemical definition of what's neutral. Now, if I measured that, what pH value would I get? Does everybody know what neutral pH value is? 7. You've heard that before. Okay, so we know that a neutral pH is 7. I'm going to tell you that depends, but we're not going to get bogged down in it. Okay, room temperature at 7. Are you with me so far? So what does it mean to be neutral? It means your hydrogens equal your hydroxides. What's the value, the parameter of pH that's neutral? 7. Okay, so what that means is if I took a beaker of water, pure water, nothing in it, and I stuck a pH meter in it, here's my little pH probe. When I look at the pH meter, what is it reading? It's got a scale from 0 to 14. Where is it? Sitting on 7. Okay? So if it's exactly just pure water, plain water, the pH is 7. Okay? But we know from our chemistry that in water the number of hydrogens is exactly equal to the number of hydroxide. So everybody nailing down the idea of what neutral pH means. Hydrogens equal hydroxide. Okay? All right. So how did we get this number 7? Where did that number come from? If you measure the hydrogen ion concentration in pure water, some of those water molecules will dissociate. They'll split apart. How many of them do that? 0.0000001 moles per liter. That's a very small quantity, right? Okay, how would I write that number in scientific notation? Do y'all remember how to do that? All right, so what do I do? Here's my decimal. I count the number of zeros. I go to make it 1, a whole number, and I count how many times I had to move that decimal. How many times did I have to move it? 7. So it's 1 times 10 to the minus or negative 7. Why is it minus or negative? is smaller than 1, okay? The negative exponent tells you a number is less than 1. All right? Questions about that? Yeah. That's scientific notation. Okay, so just a quick review of scientific notation. Just see. Ten in scientific notation is 10 to the first power. What's 100? 10 squared, right? 10 times 10 is 100, right? What's 1,000? 10 cubed. What's 1/10? 10 to the negative 1. Okay, so 100th would be 10 to the negative 2 and so forth. And so on and so forth. So when I have that many zeros, I really don't want to have to write them all. So using scientific notation is just easier. Okay? So how did I get pH? What's the pH value? It's just that exponent. Are you with me on that idea to start with? Now, it gets a little confusing when you have a pH that's 3.4, 6.8. So we're not going to go there mathematically. Just accept that you can do that. Okay? But what we have to look at next is that since things that are acid are going to lower the pH, we have to understand mathematically what we've done. So if I have something with a pH of 3, how would I write the hydrogen ion concentration of that acidic solution? How many zeros? Right? Is that a bigger number than a pH of 7? Yes. Right? 1 out of 1,000 is much bigger than 1 out of 1,000,000,000, right? Okay. So this is greater than the lower number, right? Which means there's more acid. So what is the effect of acid on pH? The pH number goes down, which means more hydrogen ion concentration, right? Okay, so the way we write that in physiology is that when we increase the hydrogen ion concentration, we have decreased the pH. And that's an important thing for y'all to remember. In A&P2, one of the first things I'm going to hit is, what's the effect of acid on pH? And what do I not want to hear? It goes up. Okay, that's backwards. More acid, the more acid you add, the lower the pH. Okay, got it? Okay, so I want to talk to you a little bit about 3 groups of acids, and we're not going to get stuck on them. But we're going to have volatile acids, and then we're going to have 2 kinds of fixed acids. Our fixed acids include mineral acids and organic acids. What does volatile mean to you? Someone has a volatile personality. What does that mean? They're violent, or they're prone to mood swings, or they change easily, okay? In physiology, volatile means you can breathe it off. That's what it means, okay? So there is one volatile acid. It is carbonic acid. How do I breathe acid? Okay, so I have a waste gas that I exhale. It's carbon dioxide. And carbon dioxide is interchangeable with carbonic acid. Is everybody okay with that idea? Got it down? So how do I get rid of carbonic acid out of my bloodstream? I exhale carbon dioxide, and that then takes away the base amount of the carbonic acid, okay? So just think of them as being just two forms of the same substance. Are you with me on that? Carbonic acid is the acidic form of carbon dioxide. It's volatile because you can breathe it off. All right, so far? Questions? Okay, mineral acids are going to be things like, I don't know, sulfuric acid, not that we really want to mess with that, or hydrochloric acid. Organic acids are things that are products of metabolism in the body, like lactic acid. No matter what kind of acid it is, what does it do to the pH? Lowers the pH. Okay? So next semester, one of the things you're going to be doing towards the end of the semester is looking at pH balance in the body. By then you will have studied all the body systems that can impact it, and you'll be able to grasp the concept of acid-base balance based on these three kinds of acids. Are you with me on what an acid is? Sort of. Okay. So if I asked you to define an acid, then you know it has something to do with hydrogen ions. And what an acid does, we say, is that it donates hydrogen ions. Acids donate hydrogen ions. In other words, they dissociate in a way that splits off a hydrogen ion. So is water an acid? Can it split off a hydrogen ion? So does that make it an acid? Absolutely it is. It's a very weak acid, but it is an acid, technically.
That would also mean it's also a base.
Yes, it is. Yeah, it is. It's an acid and a base. Okay, what about carbonic acid? This is the one I just mentioned. Where did we get carbonic acid? From CO2. Actually, we combine it with water, but right now we're looking at how it's going to donate a hydrogen ion. If it gives up a hydrogen ion, what it leaves behind is just one hydrogen instead of two, and of course it has to have a negative charge because the hydrogen ion took a positive. Is everybody okay with that idea? Questions about that? The carbonic acid gave up a hydrogen ion. That took a positive charge. So the remainder of the molecule has to be negative in order to make up for that, okay? So what do we call this? What's this called? That's bicarbonate. And that relationship between carbonic acid and bicarbonate is an important one for you to remember. You need to know the chemical structure, and you need to know what did I have to do to carbonic acid to turn it into bicarbonate. Are you with me on that idea? First and foremost, we got that? Because we're going to explore that one a little bit more, but first, let's meet a couple of other acids, well, at least one. What about hydrochloric acid? What's the formula? HCl. Cl is chlorine, or chloride in this case, because it's an ion. So what's it going to dissociate into? Hydrogen ion and a chloride ion. Okay? So we've met some acids, a few, not many, but a few. And we have the basic idea down. What is an acid able to do? Split into two parts, one part of which is always what? Hydrogen ion. Okay, whatever else is left is some kind of negative ion. An anion is a negative ion. Whatever's left is an anion. But it's always going to have the capacity when it gets in, when it's dissolved in solution, to split off a hydrogen ion. Okay? All right, what's the opposite of an acid? A base. What does a base do? A base is able to pick up that hydrogen ion. So So since we know hydrogen ions have positive charges, guess what bases have to have? Don't they have to have negative charges? They have to. Okay? So didn't we already draw some negatively charged things like OH and bicarbonate and chloride? So technically, aren't those all bases? Can they take hydrogen ions? Yes, they can. So that makes them all technically bases. Are you with me on the idea of what a base is? Okay, how likely are they to take a hydrogen ion back? Depends on their personal chemistry. For example, chloride really doesn't want it back. It's just flat, really not interested. Bicarbonate can take it or leave it. Hydroxide very strongly wants to take it. So this is a strong base. Hydroxide is a strong base. We would say bicarbonate is kind of a weak base, but that's all relative. And chloride is really not a good base at all. It really doesn't, even though it's negatively charged, it really flat doesn't want to take that hydrogen ion. The stronger the base, the more likely it is to snap up those hydrogens. Are you with me on that idea? Okay, so if we can have strong and weak bases, can we not also have strong and weak acids? Okay, so let's look at what happens when I put a strong acid in a beaker of water. So nothing in here but water, and I add in some hydrochloric acid, which is a very strong acid. By definition, a strong acid completely dissociates. So I'm going to have loose hydrogen and chloride. What did I tell you about chloride? Really doesn't want those hydrogens back. It's going to dump them as soon as it can. Every bit of it dissociates. How many hydrogen ions do I have in concentration? Just as many as I had molecules of hydrochloric acid. Completely dissociates. Okay, very strong acid. Y'all knew that about hydrochloric acid, right? So the strength of the acid depends on how diluted it is. Are you with me on that idea? So if I had a little bit of hydrochloric acid, the pH might drop a little bit. The more I add, the more pH is going to drop. Are we good with that? Questions about that? All right, then let's look at what happens when you have a weak acid like carbonic acid. When I add carbonic acid to a solution, what I find is that some of it dissociates. And of course, when it does, you're going to get these bicarbonate ions formed. But some of it won't. Some of it will stay in the form of an acid. It just doesn't all dissociate because it's not a strong acid. Is that all right with everybody? So we would draw that as a chemical reaction at equilibrium with a reversible arrow. And I've run out of room on my screen, so I'm going to put it down here. What does that reversible arrow tell you? Goes either way. Okay? Just as likely to dissociate as it is to reassociate. If I did the same thing with my hydrochloric acid, how would I draw that? Every bit of it dissociates. None of it reassociates. Everybody see the difference between a strong acid and a weak acid? Questions about that? Okay, so likewise with our bases, but remember that for carbonic acid, that bicarbonate is the base that goes with it, right? So if I put carbonic acid in solution, then what I find is that I have about equal concentrations of the carbonic acid as I have the bicarbonate. However much carbonic acid I added, about half of it will dissociate, and the other half will stay in the form of carbonic acid. That's what a weak acid does. Okay? Questions about that? So everybody has down the idea of what an acid is, what a base is, what a weak or a strong acid, what a weak or a strong base is. Good? Okay. So then we have to look at pH balance. I told you yesterday what the normal pH range is in human blood. What is it? 7 point. And it's going to fluctuate. It's going to be higher in arterial blood than it is in venous blood, systemic arterial versus systemic venous blood. Why would that be? If you know that systemic venous blood is returning blood from your tissues to your lungs, what do you do in your lungs to CO2? You exhale it. So if I have venous blood going to the lungs, and then it returns through the arteries, technically it has to get back to the heart first, but just as an overview, this is where I'm giving off CO2, right? So which one has a higher CO2 concentration, venous blood or arterial blood? Venous blood has an increased concentration of CO2 compared to arterial blood, right? Good? Okay, so what's the relationship between CO2 and carbonic acid? The higher the CO2, the more of it's going to get converted to carbonic acid. The more carbonic acid I have, the more there is to dissociate into hydrogen and bicarbonate. And of course, what happens when this goes up? Higher acid. What about the pH? Lower pH. So that going up causes a decline in pH. Does that make sense to everybody? Venous blood has a lower pH than arterial blood, all other things being equal, because venous blood has more CO2 in it. And that CO2 gets converted, some of it, to carbonic acid. We'll get the details next semester when we get to the respiratory system. Okay, questions at this point? Okay, we have one more aspect of pH balance to take into account, and that is that the body has mechanisms to keep the pH in the normal range. We use buffers or buffering mechanisms.
Thank you.
I have a box of Kleenexes up here if you need it. Okay, so, seriously? Okay, so a buffer is something that reduces the likelihood that the pH is going to change. That's what buffers do. So if I had just plain water and I added hydrochloric acid to it, the pH might drop to, say, 2. That's a really low pH. But if I had not just plain water, but water with a buffer in it, and I added the same amount of hydrochloric acid, then maybe the pH would drop to just 6 instead of all the way down to 2. Does a buffer prevent the pH from changing? No. Does it keep it from changing as much as it would if the buffer weren't there? Yes, that's what buffers do. Okay? So buffers usually occur in two forms, and we refer to these very often as buffer systems. And the main buffer system that we find in the blood is our dear old friend carbonic acid, which, as you already know, will exist in equilibrium with bicarb. So in your blood, circulating all the time, you have both carbonic acid and bicarbonate. Where did we get the carbonic acid from? It's formed by carbon dioxide. Okay? So what happens if I have in this buffer system, this is my buffer system, and if I add some acid? I can add acid in a variety of ways. I can drink coffee, Coke, juice, eat meat. Most of the foods you eat are acidic. Vegetables, some of the vegetables are more alkaline or basic, but most of the food we eat is acidic. You produce metabolic acids. Lactic acid is a metabolic acid. So generally speaking, if you have an acid-base imbalance, you're more likely to become acidic than you are to do the opposite. So you've always got a mechanism for if your blood pH becomes too acidic, you've got to have a way to counteract that. Well, what's going to counteract an acid? A base. So here's my base. And what happens when I add acid is that I just send this reaction this way and convert more of my bicarbonate to carbonic acid. Does that make sense? I'm just you could think of it as being like a little chemical sponge. It's just sucking up extra hydrogen ions. Each bicarbonate can pick up one hydrogen ion. Is that pretty clear to everybody? Okay. On the other hand, though, if I added a base, what would I do? When I added an acid, I used the bicarbonate to counteract it. If I added a base, the carbonic acid would counteract it. It would simply release more hydrogen ions to make up for the fact that more of a base is present. So everybody sees sort of how buffering systems work. Questions about that? Okay, so what we're going to come back to at the end of all this is that idea of a hydrogen ion. What is it and why does it matter? We spend a lot of our physiological mechanisms controlling hydrogen ion concentrations in the blood and therefore in the body. Why do we worry so much about hydrogen ions? Hydrogen ions are extremely reactive, chemically very reactive. What does a hydrogen ion consist of? If I had a hydrogen atom, what's a hydrogen atom made of? It's a proton and what else? No neutrons. And one electron circulating it. So one proton with one electron, that's all there is. So what's the difference between a hydrogen atom and a hydrogen ion? What did I do to get that atom to turn into an ion? I took away its electron. So what's left? Just a proton. One little naked proton running amok. Okay? Your body proteins are adapted to a certain level of hydrogen ions, a concentration of hydrogen ions that's in the normal range as we measure it, pH 7.35 to 7.45. Your proteins are perfectly fine with that many hydrogen ions around. But if there are too many or too few, proteins lose their shape. And when proteins lose their shape, they can't do their jobs. Okay? So acid-base imbalance is crucial because it affects the function of all the enzymes in your cells, and a lot of other proteins are also affected. Questions about that? All right, so we know a hydrogen ion is just a little loose proton, and that it's chemically very reactive, and it can affect the shape of proteins. All right, so that then is our overview of acid-base balance. That's the chemistry of acid-base balance. Our second category of things we were going to talk about today was polarity. And here we've got to figure out polarity, we've got to take a look at the structure of some other atoms. So I'm going to turn your attention to the periodic table, which is awkwardly placed on the other side of the room. But I'm going to show you that if you look at the columns, they're numbered usually with Roman numerals, and that's kind of a pain. So I have 8 columns that I care about, and those of you that are close enough can see the one on the far left is column 1. It says so up at the top. The one on the far right is column 8. And then there's a bunch of mess in between of things that we don't care about. So in your assignment, in your chapter summary for today, chapter 2, you're going to see which elements are assigned. And the only one you have to know in the first row is hydrogen. The only other thing in that row is helium, and we don't care about helium. Okay, so in the second row, we don't need lithium unless you're depressed, then you might take lithium. I'm not doing the chemistry of lithium. So we need carbon, nitrogen, and oxygen. I think that's all we need. In the third row, we need sodium and magnesium. We also need phosphorus. We'll talk a little bit about sulfur, even though I didn't assign it, and chlorine. And then in the fourth row, we're going to get potassium and calcium, and we're going to stop there. If you want to know about the chemistry of larger elements, then go take a chemistry class. We don't go any bigger than calcium in my class because there's no need to. There are times that we'll need to pick up on, particularly iron, for example. But when we do, we just flat don't really need to know the atomic structure. Okay? These are the only ones we need to know the atomic structure of, and we're going to focus very quickly in on just a few key items. All right? First of all, the column that it's in tells you the number of electrons that are circulating in its outermost layer. Yeah.
We just do the periodic table, right? Is that what that is?
That is a very short version of the periodic table. That's what that is. Okay? And these are the only ones that we're going to focus on. All right? So again, the column number 1, 2, 3, 4, 5, 6, 7, 8 tells you how many electrons are in the chemically reactive level. We call that the valence level. Okay? How many electrons? The row number, 1, 2, 3, and 4, tells you how many levels that atom has. Okay, let's take a look at what we mean by levels, and we'll do it by drawing carbon. If you look at carbon, you see its atomic number is 6, its atomic mass is 12. This means that it has 6 protons and 6 neutrons, and I'm not getting bogged down in that. If it is electrically neutral, how many electrons does it have to have? 6. Because protons are positive and electrons are negative. If it's going to be neutral, it has to have the same number. Are you with me on that? So if I know how many protons it has, and I know that because I know the atomic number, then I know that for carbon, there are going to be 2 electrons in the first energy level, and there are going to be 1, 2, 3, 4 in the second energy level. Okay, so how many levels does it have? 2. How many electrons does it have in its outer level? 4. So if I look back at my list, I see it has 2 because it's in row 2, and it has 4 because it's in column 4. So everybody see how to read the periodic table? That's a crash course. If you need more review than that, it's available online in the lesson for today. The columns go this way. Okay? The rows go horizontally. All right, so you tell me, for all the rest of them on this list, and work as a group, just to give you kind of a mental break, but also to help you latch down this concept. I just want to know the valence number for each one. I don't want you to draw them. You can do that at home later. I just need the valence number for each one of those. Okay? So get with a group. If you're sitting at a table by yourself, find somebody to work with. Turn around, flip around, something. 1, 2, 3, 4, 5, 6, 9, 10, 11. Okay, I'm just going to say you should be done by now. Why? Because the column number is what I'm asking you for. The column number is the valence number. The valence number is the number of electrons in the outer energy level. Okay, so let's work on it together. What was the valence number for hydrogen? 1. How do we know that? It's in the first column. Where's sodium? That's Na, for those that didn't remember that. Isn't sodium also in column 1? So isn't it also valence of 1? What about magnesium? It's in column 2. What about potassium? What is it? And calcium? 2. All right, what about carbon? It's in column 4. Nitrogen? 5. Oxygen? And what about phosphorus? 5. And sulfur? 6. And what about chlorine? 7. All right. Did you see how easy that was? On the test, I'm going to provide you with an abbreviated periodic table. because I'm more interested in you knowing how to use the table than memorizing those numbers. Okay? You're going to get good at it anyway, but just if you need to check it, it'll be there it'll be right at the top of the test. Okay, does everybody know where we got those numbers? Because that's the last time I want to look at the periodic table today. What I need you to know next, now that you know the valence number, is I need you to know how many electrons it takes for an atom to be stable. So hydrogen by itself is not stable, but it's in row 1. And level 1 things need 2 electrons. Level 2 things need 8. Level 3 things, 8 or 18, don't ask me why. It's a long story, don't ask. And then level 4, we won't care. Okay, I think it's 36, but I haven't looked it up lately. I don't care what level 4 is because I'm a biologist, not a chemist. That's what it boils down to. So can you remember 288? We really don't even need the 18. Just, try to be truthful here. 288. So that being said, if hydrogen has 1 and needs 2, it needs 1 more, or in some cases, as we've already seen, it can give up the 1 it has and become a hydrogen ion, right? So it can either lose 1 or share 1. It's going to either lose 1 or share 1. And then it's going to be happy. If it shares 1, it's kind of like a timeshare. If it shares 1, it makes 1 bond. Okay? So how many bonds does hydrogen make, whether it loses its electron or shares its electron with somebody else? It makes 1 bond. Are you with me on that? All right, let's see what we can do with the rest of those guys on our list. What about sodium? It has 1 in level 2. It needs 8 if it wants to fill level 2. How likely is it to find 7 electrons somewhere? Not happening. Okay, so it's going to lose it. Everything in level 1, or in column 1, everything in column 1 is going to lose 1 electron. And hydrogen is the only one that could also share. Make sense? I'm hoping this is a review. And I'm trying to get through it to polarity as quickly as I can. What about magnesium and calcium? Where are they? They're in column 2. They would need 6 more. Not happening. So they're going to lose 2. Okay? All right. Let's focus in on the guys that we need. Carbon, nitrogen, oxygen, right in the middle of things. Those are the ones I want to focus on. And I'm just mindful of the time and that we have to get to polarity, which is where we started with this. So carbon has 4. How many more does it need? 4 more. So it's going to make 1 bond for each electron that it needs. So that being said, how about nitrogen and oxygen? Nitrogen has how many? So how many more does it need? 3. So it makes 3 bonds. And what about oxygen? Is everybody seeing the logic here, this progression? We had 2 bits of information. We knew the valence number, but we also knew how many electrons it took for that atom to become stable. 2 in the first level, 8 in the second, 8 in the third for these small atoms. All right, so where are we going to go from that? Well, carbon, if you look at carbon, if you look at it 3-dimensionally, carbon has 4 potential spots for bonds to be made. And if we bond it with something that's very easy to find, both on paper and in the real world, we can bond it with hydrogen, and you see what you get is methane, which is a perfectly symmetrical molecule. Does everybody see how that works? Questions about that? Okay, so what would I do with nitrogen and with oxygen? See if you can draw those. I'll return you to my drawing of methane. Okay, while you're working on that, I'm going to walk around with this model that shows you the shape of that atom with the 4 bonds. You see it's kind of a pyramid shape? All right, so here is the three-dimensional structure of those 4 bonds. So they're not just flat, so it's got 3 dimensions. Kind of curious. All right, so this is what those 4 bonds look like. Whether it's a carbon, oxygen, or nitrogen, it's got 4 places where bonds can be formed. Okay, so it's not flat, it's not flat. Okay, so here's the 3-dimensional structure. It's not a flat bond. 4 spots for bonds. That's the structure of a molecule. That's the 4 bonds. Okay? All right, so what does ammonia look like? It still has 4 spots. How many electrons did nitrogen have of its very own? How many electrons does nitrogen have? 5, right? 1, 2, 3, 4, 5. So these 3 need a partner. And I'll stick a hydrogen there because remember, hydrogen is very happy to bond. Okay? But I still have these 2 electrons sitting here by themselves that did not get combined with a hydrogen. Are you with me on that idea? Okay, so then what about oxygen? It has 6 electrons, 1, 2, 3, 4, 5, 6 electrons of its own, and only 2 of them that need a partner. So that's how you make water. Are you with me on that? 3-dimensionally, is water a flat molecule? I just walked around with the little model. It's not flat. It's got these 2 spots that have its own electrons. And these electrons, because of the nature of oxygen, that oxygen atom is very electron hungry, so it's electronegative. If you look at the structure of a molecule of water, if that's the oxygen atom, and here sits a hydrogen atom and another hydrogen atom, looks kind of like Mickey Mouse ears to me. Then what we find is that this side of the molecule of water tends to have a slight negative charge, whereas where the hydrogens are tends to have a little bit of a positive charge. And so we say that this molecule has poles. It has a negative pole and a positive pole. And so what do we call a molecule that has poles? Polar. And what about the bond? It's a polar bond. And that's what polarity is. So polarity is based on this imbalance of electrical charges. And we see polarity in oxygen bound with hydrogen, and we see it to some degree in nitrogen bound with hydrogen. Are we going to see it with carbon and hydrogen? No, it's a symmetrical molecule. There are no naked electrons on it. So when we get into biochemistry, what we see is that we have a lot of bonds between carbon and itself, or carbon and hydrogen, very common in biochemistry. We see some bonds between carbon and oxygen and carbon and nitrogen. Let me try that again. But if those oxygens or nitrogens also have a bond to a hydrogen, then we have bonds with some polarity. Those are polar bonds.
So all hydrogen bonds are polar bonds?
A hydrogen bond is coming up. It's not the same. Okay, so if these are polar bonds, what do you want to call the other guys? Non-polar. Okay? Does everybody understand how we got where we are just by looking at atomic structure and how electrons behave? So you have a short list of polar bonds to learn. What is your list? What does your list consist of? Oxygen and hydrogen and nitrogen and hydrogen, and that's it, folks. Okay, NH and OH, those are your polar bonds. There are others. Eventually we might add a third one, not anytime soon. And I don't have enough of these to go around, so you're going to have to combine if you're a short table, work with somebody else. But you may open these. Red is oxygen, white is hydrogen. Gray is carbon, green is sodium, no, green is chloride, and blue is sodium. So if you're not at a table with toys, just relocate to a table that has some food. And my first question for you is, what is the little guy that's red and white that you have so many of? That's water molecules, and oxygen with 2 hydrogens. And the next thing I want you to do is explore their behavior. How do they behave? They do have magnets in them. It's not magic. Sorry to disappoint you. All right, so tell me what happens if 2 water molecules approach each other, oxygen to oxygen. What are they doing? They repel. What about hydrogen to hydrogen? They repel. What about oxygen to hydrogen? They attract each other, right? Just like the poles on a magnet, that's exactly what these are. These are little polarized magnets that they stuck in these models. So what we know from atomic structure is that the oxygen is a little bit negative and the hydrogen end of the molecule is a little bit positive. And we also remember from 5th grade or wherever that like charges repel and opposite charges attract, right? So when you get these water molecules behaving in a way that causes them to interact with each other, what you find is that they'll actually reorient themselves so that the oxygen of one end will be attracted to the hydrogen of another. So if this is the hydrogen, then the oxygen of the other molecule Come on. Will be attracted to the hydrogen of the first. And so you can actually see how many of them you can string together and hold up in the air. Can you get the whole line of them going? So the bonds, of course, on our toys, they're magnetic bonds, but the bond between the hydrogen of one molecule and the oxygen of another molecule, that's the hydrogen bond. Okay, so you remember I told you that the green is chloride and the blue is sodium, right? Who are they attracted to?
Each other.
Okay, are they attracted to water at all?
They're attracted to hydrogen.
Both of them? So sodium has what kind of a charge?
Hydrogen.
It's got to be either positive or negative.
Positive.
Sodium is positively charged. How do we know that? Because we know it's in column 1, and it gives up an electron, making a positively charged sodium ion. It's got a positive charge. So which part of the water molecule will the sodium be attracted to? The negatively charged oxygen. Prove it. Does the little blue ball attract to the oxygen? It's supposed to.
The oxygen, yes.
The oxygen, yes. The hydrogens, no. What about the chloride, the big green ball? It's not only attracted to the sodium, it's also attracted to the hydrogens. Okay? Ions are attracted to other electrically charged things. So if you have something that's polar, like water, it's also attracted to ions along with other polar molecules. So what would it not be attracted to? Non-polar things, your little gray thing in there, which is probably just a partial molecule. Is it attracted? Gray is for carbon in this particular set. Okay, so things that are polar are also called hydrophilic. What does that mean? Water attracting. And things that are non-polar, phobic, repelling. Does everybody understand polarity? Depending on your age and personal makeup, your body is somewhere between 70 and 92% water. So how important is the polarity of water to you personally? Yeah, you need to understand the polarity of water. Okay? Questions about that? All right, just to avoid temptation, would you mind putting the toys back in the cup? And we're going to jump to a category of molecules that, as a class, are nonpolar. I didn't lose any salt. All right, so tell me how much oxygen, hydrogen, or nitrogen-hydrogen bonds there are going to be in something that's a lipid. A lot or hardly any?
Hardly any.
Hardly any. What were our two polar bonds that I just assigned you to learn? Oxygen, hydrogen, and nitrogen, hydrogen. So I must not have a lot of those in a lipid if lipids are nonpolar. So everybody got that okay? So lipids are composed mostly of carbon to carbon, carbon to hydrogen bonds. They can have other things appended to them. There's a little bit of oxygen, but not a lot. I'm assigning you to learn the different categories of the lipids. We're going to focus in on one particular group of lipids. We're going to start with the triglycerides. And if something is a triglyceride, you know it has three of something, right? So a triglyceride is composed of 3 fatty acids. Attached to a molecule called glycerol. We're going to take a look. We're going to look at glycerol first, but when I attach fatty acids to glycerol, it takes away its polarity. So glycerol has 3 carbons. Each carbon has some hydrogens stuck to it. Remember, each carbon has to have 4 bonds. So there's glycerol. Would you say it's polar or nonpolar? It has certainly carbon-carbon bonds, it has carbon-hydrogen bonds, but what else do you see? 3, those are hydroxyl groups. OH is the hydroxyl group, and OH we know is polar, right? So if I put glycerol in water, would it mix? Glycerol in water? Yeah, it mixes. By the way, it's okay to play with glycerol. Glycerol is one of these weird molecules that's polar on one side and not polar on the other side. And that's what they put in bubble mix. Summertime, good time to play with bubbles. Yeah, you can go to the pharmacy and buy a bottle of glycerol. It'll last you forever. Put a little bit in your kids' bubble making stuff. It makes the bubbles get bigger because of its polar, non-polar mix. Okay? That's what, when they make the giant bubbles in the shows, that's what they're using. It's not that expensive either. Okay, so you're allowed to play with glycerol. You're not allowed to play with everything that we talked about in here. All right, so, but when I take glycerol, and I'm not going to draw the hydrogens because they get in the way. So we're just going to assume they're there. I'm going to take that oxygen that I just said was polar, and I'm going to stick it to a big, long fatty acid, which means I'm going to take the hydrogen off of the oxygen. So I took away the polarity of glycerol when I stuck 3 fatty acids on it. Are you with me on that? So is glycerol polar now? No, it's a glyceride. Now, in fact, it's a triglyceride now because I stuck 3 fatty acids on it, and then everywhere I stuck a fatty acid, I got rid of a polar bond. So it's not polar anymore. So what we have to look at next is, well, what is a fatty acid made of? Well, let me show you what a fatty acid is. First of all, it's an acid. So at one end, it has to have our soon-to-be favorite acid group. This is the carboxyl group, also called the carboxylic acid group. Why is it an acid? What does it take for something to be an acid? Do I need to flip all the way back to that page? Has a hydrogen that can break off as an ion, right? Do you see the little hydrogen right there? That sucker can break off. Right now it's not broken off, so I have an acid here. All right, but that carboxyl group is attached to a big, long chain of lots of carbons, and those carbons have nothing else but hydrogens attached to them. Does everybody understand what the little dots mean? Those little dots mean I ran out of room to draw more. So a short fatty acid will have 14 carbons. That's a short one. Can have at least up to 28 carbons long. So you can see why I didn't want to draw it all. Every one of those carbons has nothing attached to it except hydrogens. That's it. And so I've got this big long chain of nothing but carbons and hydrogens. Is that polar or nonpolar? That's about as nonpolar as you can get. So that's the structure of a fatty acid. A carboxyl group at one end makes it an acid, but the fatty part of it is a chain of 14 to 28 carbons and hydrogens. Is everybody okay with that concept? It's a big molecule. And does it mix with water or not? Do fats and water mix? Oils and water mix? No, it doesn't mix. It's nonpolar. So even though, yes, I've got this little polar area here, it is totally outweighed by the fact that I've got 14 to 28 carbons just kind of dragging it down. Okay? Questions about that? And when I attach that to my glycerol, I attach it with that carboxyl group. So what happens to the polarity of my fatty acid? Just that one little part was polar. And I took it off. I took the polar part off of it when I attach it to the glycerol. So when I attach a fatty acid to glycerol, all I have left is an oxygen without a hydrogen attached. And I got rid of the polar part of both the glycerol and the fatty acid. So how much polarity is left? Like none. Okay, so a triglyceride is a fat or an oil. It's a nonpolar molecule, pretty much totally nonpolar. And therefore, is it hydrophilic or hydrophobic? Phobic, hydrophobic, water repelling. Are you with me on the chemistry that got us to where we are today? Okay, good? Okay, one more little piece of information and then we're ready to start building something with these. The difference between a fat and an oil. This will come in handy in the kitchen as well as on your test. Does anybody know the difference between a fat and an oil? Solid versus liquid at room temperature. Okay, so if you're cooking and you have to pour it, it's an oil. If you have to scoop it, it's a fat. Or slice it, or whatever. So butter's a fat, Crisco's a fat, lard is a fat, olive oil is oil. Duh. Okay. Chemically, what's the difference? They're all triglycerides. The chemical difference has to do with whether the fatty acids are saturated or unsaturated. So we're going to look a little bit at the chemistry of that so you can see why that makes a difference. And then we'll apply it actually to a real cell, well, to a drawing of a cell anyway. All right, so if it's a fat, then the fatty acids are saturated. For a fatty acid to be saturated means it's full. Saturated means full up, okay? Which means in the case of a long chain of carbon and hydrogen, that it's full of hydrogen. It's got all the hydrogens it can hold. And that end carbon is the one that's attached to the glycerol. So that's saturated. It's full of hydrogens. Are you with me on the idea? It's got as many hydrogens as it can. How would I unsaturate it? What would I have to do to make it unsaturated? I've got this thing called a double bond. Carbons can share 2 pairs of electrons instead of just 1. They still only make 4 bonds. So for all of the carbons that have only single bonds, they are still going to be full of hydrogens. But what about these guys that have, a double bond? There's a spot there where it doesn't need a hydrogen. That's not an oxygen, that's just an empty spot. So why do I call it unsaturated? It's not full. It has 2 fewer hydrogens than it would if it were fully saturated. Every double bond a fatty acid has is a spot where it is unsaturated. If it has only 1, we call it monounsaturated. What if it has a bunch of them? That's polyunsaturated. And that has 2 effects. One is on the shape of the molecule, and the other is on how many calories it is. The more hydrogens, the more calories. Saturated fats have more calories. They have more energy. Unsaturated fats have less calories, less energy. Hydrogens carry energy that can be converted in the body to useful forms or stored for later. Okay, so that's the effect on the energy. The effect on the shape is this. If I have a saturated fat, then the carbons in 3 dimension kind of form a little zigzag pattern. But if I have one that's unsaturated, then for every spot that it's unsaturated, the bond angle changes. And it forms a little kink. So unsaturated fatty acids are kind of kinky. And the effect that has on the fat molecule, here's my little glycerol, here are my 3 fatty acids. If I have one that's unsaturated, what happens is it kind of has a kink wherever there's a double bond. So in 3 dimensions, it doesn't pack as tight. So if I have a saturated fat, then every little molecule is just nice and linear, and they can pack up nice and tight and form a solid at room temperature. But for every kinky fatty acid I've got, that makes my molecules tend to kick each other away from each other. They don't pack as tight. So what happens? They form a liquid at room temperature. Kinky fatty acids won't pack tight. So they cannot be solid. They cannot form a solid. Does that make sense? Questions about that? Does everybody understand how we got there from the chemistry we started with? Boy, there's a lot. Okay, so what difference does that make in terms of the use of lipids in your cells? Well, it turns out it makes a big difference. So if we look at the form of a typical cell membrane, and you may have learned this in intro, or you may remember it from somewhere else, that your cell membranes are a lipid bilayer. What does bilayer tell you? There's 2 layers. So I'm going to have 1 layer of lipids and then a second layer of lipids. And that's going to make the cell membrane. Questions about how we got there? We're going to come back to see how we made the cell do that, but do you see what the lipid bilayer is? If these were all saturated fatty acids, they would pack tight and form a solid. We really don't want our membranes to be solid because if they're solid, they're not very flexible and they tend to break instead of bend. So what we really want is for our membranes to have a kinky fatty acid. What's that going to do to my membrane? It's going to make it a little bit more flexible. And now it's more fluid and will bend when you push it instead of popping. Okay, does everybody see how important it is that some of your fatty acids are unsaturated? Questions about that? Okay, so we're going to come back around to the important idea of polarity and the effect it has on these membranes. because you would not be alive today if it weren't for polarity and non-polarity and how they interact with each other. So instead of building a fat now, we're going to build a second kind of lipid called a phospholipid. Can you tell me what a phospholipid is going to have in it? It's going to have some phosphorus. And so it's going to have one part of the molecule that has a phosphorus. Phosphorus is almost always attached to oxygens. And I'm just going to show you this once. And after that, we're not going to worry about it. This is a phosphate. How many bonds does phosphorus make? Does everybody see 5? Yeah. Where's phosphorus on our periodic table? It's right below nitrogen. How many bonds do you want it to make? 3. And it's making 5. Okay? We're just not going to go into chemistry deep enough. I made the mistake once of asking one of our chemistry professors to explain chemical structure like this to me. Half an hour later, he finally admitted they really didn't know how it worked. But he spent half an hour trying to explain it to me before he gave up. So we're not going there, okay? You need to recognize phosphate when you see it. You need to see that it has a double bonded oxygen. You also need to know that one of those oxygens can attach to a nice glycerol molecule. And that glycerol can also be attached to a couple of fatty acids. But this other oxygen can be attached to this big humongous thing called, it might be choline, might be serine, might be some other things, that very often has a nitrogen in it. And that nitrogen can be polar. And of course, this oxygen here needs another bond, but it might be ionized. So when we look at the phosphate-containing part of the phospholipid, it's polar and partly ionic. So is it hydrophilic or hydrophobic? Philic. And what about our fatty acids? Phobic. So what we have when we make a phospholipid is we have this molecule that we're just going to kind of abbreviate as something that looks kind of like this. And one of my fatty acids is kinky and the other one is straight. And the phosphate containing part we call the phosphate head. And it's polar and therefore hydrophilic. And my fatty acids are my fatty acid tails. And of course, they are nonpolar. We've come a long way. If you get this, if you understand what we've done so far, you're in pretty good shape right now. If your brain's starting to tickle in the back because you're like, I'm not sure I followed this, then don't be alarmed. Because when you go home and go through chapter summary for chapter 2, it's going to go back through it again for you. Okay? All right, so what am I going to do with these phospholipids? These are the guys I'm putting in my plasma membrane, my cell membranes with that lipid bilayer. So if I just, in an experiment, we won't do this in real life, but if I took a beaker of water and I poured very carefully over the surface of that a thin layer of phospholipid right over the top of it, draw for me in your notes, I'll just come around and look, draw for me what the surface of that water is going to look like. Each phospholipid molecule looks something like this. Draw a layer of phospholipids over the surface of the water. It's okay to look on at your neighbors. right, so you remember which part of the molecule is hydrophilic and which part is hydrophobic, right? So which part's in contact with the water? The heads, right? We've got heads and tails. Heads or tails? Heads. Where are the tails? They don't like water, right? So where are the tails? Up in the air, right? Phosphate heads in contact with the water. Tails. They might be kind of laying over each other, but they're not going to be in the water, right? Because water repels them, right? Does this spontaneously just based on its chemical nature. All right, what you need to do next is stir that until you get little droplets of phospholipid in the beaker. What is one droplet going to look like? Remember, it has water all the way surrounding it. So what part of the molecule is in contact with the water, and where is the other part? What part likes the water? Heads. So if I've got water around it, then don't the heads need to be? Yes. And then where are the tails? They're not sticking out, right? Because they're surrounded by water. They're all hiding in the middle. Okay, so that's phospholipid droplet. Does that make sense to everybody? Did I have to force them to do it? Encourage them, coax them, explain their own chemistry? It does it spontaneously. Okay, now last step. We've got to take one of those phospholipid droplets, think three-dimensionally, and put a droplet of water on the inside because that's going to mimic what our cells look like. So if this is your phospholipid here, in a sphere, like a soap bubble, how are those individual molecules going to be arranged? Okay, see if you can draw that. I don't have to draw the whole thing, but at least get it started. So usually if you can figure out where your phosphate heads are going to go, you know they like water, right? So where do the heads go? What do you mean middle? Are they going to go on the outside? All of them? Don't I need some on the outside? So wherever there's water, I need phosphate heads. Does that make sense? Okay, then where are the tails? The tails are in between the two layers of heads. Does everybody see how that works and why it is? So if I just took a piece of that membrane and looked at just one segment, what would I have? Phosphate heads on the outer side. That's in the body extracellular fluid. Phosphate heads on the inner side. That's the intracellular fluid. Fatty acid tails in between, hiding from the water. Does everybody see how I did that? Just based on its chemistry. Based on the idea of polarity and non-polarity. So all of this idea of the lipid bilayer, which we had already said is the way cells are arranged, their membranes are arranged in a lipid bilayer, is based on the polarity and non-polarity of the two parts of the phospholipid. Okay? Don't have to be alive, just does it. Yeah?
Are the tails touching on
Are they touching each other? I've seen computer models of them, and yes, they do come in very close proximity. They probably don't overlap, but if you wanted to look at something that looked more realistic, you can Google images and see some, but if that's what the phosphate head really looks like, and this is a fatty acid tail and another one, the guy on the facing side is going to come pretty close. So is there a gap in between? No, no gap. Usually you see in the pictures when they draw them, there's like this empty space in there. No, that's not real. They really do just basically touch each other. Are they stationary? Are they frozen in time or space? No, they're not solid. Remember, this is a lipid, it's a fluid membrane. They're moving. They move because of kinetic energy. Okay? So that whole idea of this bubble that forms, it makes your all of the membranes of your cell, these membranes form spontaneously. And as a cell forms new membranes, as the membrane accumulates, it tends to just kind of pinch off and bubbles all by itself. Okay? Does everybody understand the chemistry of a phospholipid bilayer and how that relates to polarity? Questions about that? Okay, just as sort of a application of that, I want to talk just briefly about cholesterol as another category of lipids. Because it's a lipid, what do you know about its chemistry so far? It's mostly made of carbon and hydrogen, right? Has maybe one little polar bond, and that's it. Cholesterol actually exists in the form of a ring structure. You are not going to be asked to draw it from memory. So that's sort of what the carbons look like. There are some more carbons in there somewhere. But when it forms a ring like that, usually we just abbreviate it. And wherever there's a corner, there's a carbon. That's pretty common in biochemistries. Corners are carbons. And in the case of cholesterol, I think there's a little oxygen right here. And the rest of it is just carbon and hydrogen. So it has one little polar bond, and all the rest of it being just carbon and hydrogen is nonpolar. Okay so far? Okay. I'm going to use cholesterol as the base for making all my steroids. And you've got a little bit of a laundry list of steroids to learn. There's some steroid hormones. Can anybody name one or more? The sex hormones, testosterone and estrogen, progesterone. There are others, the stress hormone, cortisol. There's some others. Okay, so steroid hormones, including the sex hormones and cortisol, and anything that's called a corticoid is a steroid hormone. Vitamin D is made from cholesterol. Vitamin D is actually turned into a steroid hormone called calcitriol. Okay, so vitamin D is made, you knew you made vitamin D in your skin, right? Remember hearing that? Start with cholesterol. Okay, cholesterol is converted to vitamin D, and vitamin D is then converted into this hormone called calcitriol, which is a steroid hormone. Those are all steroids. And then another one is called the bile acids. And bile acids are also called bile salts. And basically, to make a bile salt, you take cholesterol and you stick an acid on one end. cholesterol, you know, is very nonpolar. Acids, of course, react with water quite well. So when you have a bile salt, then you have something that is hydrophobic on one side and hydrophilic on the other side. And that makes it mix with the fats in your diet and also mix with the water in your digestive juices so that your fats are dissolved and handled by your digestive system. That's the job of the bile salts. Okay? So that's just a short list of what some other lipids are in the body. Steroids all. Okay? So what did we start with to make steroids? We started with cholesterol. There are some other lipids that I'm just going to leave for you to read about for a couple of reasons. One is the application of them is way down the line, and I don't want to get bogged down in it too much. I do want to talk a little bit, though, about proteins, and when we do, we are going to relate this to the idea of polarity. So you need to know the basic structure of a protein, you need to know the basic structure of a protein's building block, and you need to know why polarity matters to that. Are you with me so far? So what are proteins made of? Amino acids. And to make a protein, I just string amino acids together in one long chain, and then I can take those chains and combine them in different ways to make different proteins. Okay, so it's just amino acids stuck end to end, not branched, not all gobbled up, just end to end in a linear arrangement. Okay, so what does an amino acid look like? Every amino acid has certain features in common, and then each amino acid has a unique feature as well. So to draw an amino acid, we start with what we call the central carbon, and on one side we put our favorite acid, which is our carboxyl acid. And on the other side, we put an amino group, which is very close to ammonia. So we have amino acid. Does everybody see what we have so far? The amino group is always NH2. The carboxyl group, we usually abbreviate COOH. Am I done yet? What about that central carbon? How many bonds does every carbon need to make? Always 4. So one of those 4 is always going to be a hydrogen, and the other one is always going to be something different for each of the different kinds of amino acids. So we use the term R to just refer to the rest of the molecule. All right, so I can use this pattern for any amino acid. They all look the same in that regard. The problem is those R groups are always different. In human chemistry, we use 20 different amino acids to build our proteins. I want to tell you there are more than 20 kinds of amino acids, but we use the same 20 that almost everything else alive today uses. 20 amino acids are the building blocks of proteins. Some of them can be modified later. We're not even going to go into that. 20, that's our number. So how many different R groups must there be? 20 of them. And we can categorize those R groups into different groups. Some of them are hydrophobic. Some are hydrophilic. Some are acids. Some are bases. There's a couple of them that contain sulfur. And then there are some that just don't really fit into any of those categories. The secret to making a protein that does what you want it to do is to use the correct 20 amino acids in the correct sequence. Okay? So let's take a look at what that would look like. If I have amino acid 1, and it's sitting here with its amino group here, and its carboxyl group here, and we'll just call it R1. And I want to combine it with a second amino acid, Everybody see my 2 amino acids? Here's one. Here's the second one. See the amino groups? You see the acid groups? So what I'm going to do is I'm going to take this out. What is that? That's water. So I'm going to pull water out. Okay? What's it going to look like when I pull the water out? Does everybody see that carbon needs a bond and that nitrogen needs a bond? And they're just going to get stuck to each other. And we call that a peptide bond. So when you stick 2 amino acids together, you make a dipeptide. What if I stuck 3 amino acids together? What if I stuck a bunch of them together? Polypeptide. And in general, proteins are polypeptides. Some of them can be short, some of them can be long, but this is the way you make proteins. Stick amino acids together end to end, amino end to carboxyl end to end to end. And what you wind up with inevitably is a long chain of amino acids all stuck together, and all of them having different R groups. And depending on what those R groups are, that will determine what happens next. And if I have 100 or 150 or 400 amino acids all stuck together, I'm still going to have this linear molecule, no matter what amino acids those are. So imagine that this is my amino acid stuck in the end. I've got 20 amino acids here. Okay? What happens next depends in part on what the R groups are, but it also depends on the amino groups and the carboxyl groups that are still there. And what those tend to do is to make this thing coil. It will just coil up while it's being made. So as the amino acids, as enough of them stick together, this thing will coil. It's not very well coiled, but it's supposed to look sort of like a spiral staircase. We call it a helix. Okay, so it's going to coil. Most of them do. All right, so once it's coiled, though, imagine that the R group here is hydrophobic and the R group here is hydrophobic and all the other R groups are hydrophilic. What's going to happen next? This thing's in water. Hydrophobics don't like water, so what will they do? They will fold up and it will connect. And if this were also hydrophobic, then it would likewise fold up. And this little guy might fold up. And so what you end up with is a protein with a characteristic shape based on what those R groups were. The folding pattern is based on the R group. So what would happen if I had a mutation that made that, instead of a hydrophobic R group, it was a hydrophilic one and it didn't fold properly? Yeah, I just mutated that into non-functionality. It won't work? Won't work. Does everybody see the importance of the R groups? Questions about that? Okay, so next class period, we're going to be working on cells. When we do, we're going to look at, again, the functions of the chemistry of the cell membrane and the functions of the proteins. We're going to spend some time on what happens when things go wrong, when mutations occur. What happens when membranes don't work the way they should. It would be nice if you could, between now and then, review the basic organelles. There's actually a practice quiz just on organelles. Remember, your practice quizzes don't count for grade. You can take them as many times as you want. And I'm not going to lecture on the parts of a cell. You learned them in high school, if not before or after that. So make sure you've gone over that. Okay, questions for today? All right, before you leave, I've got a few minutes left. Within your group or individually, whichever way you prefer, I want you to reflect on where you got lost today, if you did, what you need me to go over again, what questions you might have. I need a sheet of paper from each and every one of you. Well, I can have, if you're working together, just make sure everybody's name is on one sheet of paper. So I need at least one sheet of paper from each table with first and last names clearly written, please. Table number on the sheet as well. And either what wasn't clear, what questions you have, what you need me to go over again, which I may or may not actually do. Or if everything was clear, tell me that. If it was all review for you, let me know. Okay, so just spend at least a minute giving me some feedback on today's lecture. And by the way, I have recorded this lecture, and I'm going to try to figure out how to post it online for you. I have a short version that's about 20 minutes that I'm pretty much ready to post. It's sort of a summary, short summary, but I also have this whole lecture recorded, assuming the iPad picked it up, and I'll post it for anybody that wants to review it, if possible, if I can figure out how to do that. All right? So as soon as you're done with that, just leave the paper on your table. I'll come around and pick them up, and if you have individual questions, feel free to come up and ask.